Hello, everyone, and welcome to Chemistry Workshop. In this episode, we'll look at the total synthesis of Jujuyane, featuring the amazing insight in how the eight-member ring in Jujuyane can be constructed from the oxidoberyllium dimer, a little studied, highly functionalized, and rigid basis for total synthesis of cyclooctanoids. Jujuyane is a natural cyclooctanoid isolated from the plant Stevia jujuyensis, a sesquiterpenoid. It is derived from an atypical skeletal rearrangement from germocranolite. Equipped with five stereocenters with one of them quaternary and a transfused lactone ring, the functionalization around this eight-member ring could be anticipated to be difficult. In addition, the eight-member ring, being one of the medium-sized rings, could be quite hard to form through cyclization due to the high ring strain and medium rings. However, the Lie group ingeniously solved most of the problem through the use of an oxidoberyllium dimer, which has functional groups arranged around the eight-member ring quite similar to that of Jujuyane and already possesses an eight-member ring as the basis of the total synthesis. First, let me introduce the use of oxidoberyllium ylides and its dimer in synthetic use. Oxidoberyllium ylides by itself can undergo a 5+2 cycloaddition with a dipolar which is a widely used strategy to construct seven-member rings in total synthesis. It is amphiphilic, being reactive towards electron-poor, electron-rich, and also strained alkenes. It has similar trends in endoselectivity akin to that of diazolder, though the latter often exhibits better stereoselectivity. Also, some examples with asymmetric alkenes show that regioselectivity manifests itself in some cycloaddition reactions with an oxidoberyllium ylide, and studies with fulvium derivatives found that 6+3 and 3+2 cycloadditions are all possible under different reaction conditions. Other studies found that asymmetric cycloadditions are possible with asymmetric catalysts. One example is shown here as this nickel catalyst. The synthetic utility presents itself in that it can undergo ether bridge opening to result in a seven-member ring or cleave one side of a carbonyl to result in a furan-based ring structure. Furthermore, fused ring systems could be formed from a tethered alkene to the precursor of this oxidoberyllium ylide. Oxidoberyllium ylide was first discovered when investigating the reactivity of a thiopuryllium species. Following treatment with phenolithium and exposure to the atmosphere, the peroxide species that would undergo elimination under gaseous hydrogen chloride, and form an oxidoberyllium ylide is found. Later, it is found that there exists a photoinitiated interconversion of oxidoberyllium ylides with epoxy indenones too. However, current generation methods are simpler and easier to access than the two mentioned. The most widely used is through elimination of acetoxypyrones. Acetoxypyrones are first generated in a three-step process from furfuryl alcohol through a method reported by Ashmatowicz in 1971. I butchered his name here, sorry, and eliminated either through heat, base, or acid. Also, it was observed that without an excess of dipolar the oxidoberyllium ylide formed would undergo a dimerization reaction, which we will also talk about later. Another method for generating oxidoberyllium ylides that is quite commonly used is generation from 3-hydroxy-4-pyrones. 3-hydroxy-4-pyrones could tautomerize into an oxidoberyllium ylide species, which formed in situ can undergo further cyclizations. However, this could mostly only support intramolecular cyclization when the isomerization is carried out by heat, limiting its utility. However, it has been discovered that methyl triflate can be used to form a protonated oxidoberyllium species, which itself can undergo cyclization after deprotonation, and then the reaction can proceed at room temperature and allows for intermolecular cycloaddition. Other methods include diazo transfer chemistry, a widely used method to generate carbonyl ylides, but some challenges render this method less successful in its utility and the synthesis of diazoketone precursors. Another one is from 3,4-diazocyclopentadienones, which can react with alkynes and undergoing rearrangements result in oxidoberyllium ylides. As previously mentioned, oxidoberyllium ylide can undergo dimerization when exposed to base with a 5+3 cycloaddition, selectively forming this endodimer. This dimer, possessing great synthetic potential, can be a source of eight-membered rings in total synthesis. The dimer, when formed, could be transformed into a series of frameworks for other ring systems too. is found to give different products when undergoing reduction by hydrogen and palladium on carbon in different solvents, with aprotic solvents only reducing the alpha beta unsaturated ketone, while protic solvents also undergo transaminase attack to form an aldehyde product. The eno ether in the ring could be also cleaved under acidic conditions, leaving behind an 8-member ring core in which the ether bridge can be cleaved under potentially potentially cleaved under previous mentioned methods, providing a novel way to synthesize 8-member rings, and that is also the method used in this paper by the Lee group. Now, going back to the total synthesis of Jujuyane, we first analyzed the retrosynthetic pathway proposed by the group. The group first noticed that the arrangement of functional groups around Jujuyane is quite like that of the oxidopyroleum dimer, so they decided to base the retrosynthetic analysis from that. The molecule Jujuyane could be constructed from two with esterification, possibly a Mitsunobu reaction to invert the stereochemistry at C8, and alkylation at the alpha position on the transfused lactone ring. Cleaving the ether bridge, methylating the alpha position of the carbonyl on the main ring, and oxidizing the acetal to a lactone could afford 2 from 3. Noticing the structural similarity of 3 and 5, the group anticipated that Barton deoxygenation and alkylation at C10 could afford 3 from 4, which can be attained from the oxidopyroleum dimer 5 by cleaving the eno ether and forming the lactone ring. Thus, the synthesis commences with the preparation of the oxidopyroleum dimer 5. The group decided to generate the intermediate oxidopyroleum yliid from base catalyzed elimination of an acetoxypyrone, which is synthesized from a reported procedure by Akhmatowicz. Perfluoroalcohol is first exposed to bromine and methanol to form 6, which then undergoes a rearrangement in aqueous acid to form the hydroxypyrone 7, and a final acetylation afforded acetoxypyrone 8. Then, according to experiments done by Hendrickson and Farina, treatment of 8 in dichloromethane with triethylamine produced the oxidopyroleum dimer 5. Then the oxidopyroleum dimer is first reduced to get 9 with dimethyl H, and then the eno ether is cleaved under acidic conditions to form a dimethyl acetal 10. Then intramolecular acetylation affords tricycle 11 from 10 with treatment of pyridinium tosylate and 5 extramolecular sieves. Then oxidation with manganese dioxide and reduction with hydrogen and palladium on carbon affords an intermediate 4 from 11, which then reacts with O-phenylcarbonyl chloridothioate to afford carbonyl 12, and a Barton-McCombie deoxygenation finishes to afford 13. For the methylation at the alpha position using methyl iodide under basic conditions, the intermediate 14 then results. Then the group explored reaction conditions for the single-step vinylation. Originally, they treated 14 with the lithium HMDS at -78 to form the enolate, and with vinyl selenobenzene to try and achieve the vinylation. However, the group discovered that 3 possible products could be found, namely 19, 3, and 20, 19 being the double vinylated product, and 20 being the vinylated product. However, when the anion attacked diselenobenzene and formed a substituted alkene. However, only 3 is the desired vinylation product here. The 3 pathway through these 3 products mainly differ in what is a carbanion attack after forming the adduct, and to eliminate side product formation, the group tested out a series of vinylation conditions with differing the base and amount of base, and the group tested with water and dimethylamine as additives for providing proton sources. At last, they found out that using 0.2 equivalent sodium HMDS as base and dimethylamine as proton source could afford 3 from 14 with 96% yield. The group then anticipated a samarium iodide single electron reduction could result in a ring opening akin to some previous research, but due to ring configurations, a vinyl group shift occurred instead to form 23. Thus, the Lee group chose to open the ether bridge with concurrent alkylation in 3 steps. 3 is first iodomethylated with iodomethane and LDA to get 24, then a reduction with TMS protection affords 25, and finally elimination with kurt-butyl-lithium as base results in alkene 26. Then we arrive at the final stages of this total synthesis, namely in reducing the isocyclic double bond, oxidizing the lactose to a lactone, and inverting the configuration at C8. However, when the group originally tried to reduce the double bond at C4, all methods failed to reduce it over the vinyl group at C10. Thus, the group tried to protect the vinyl group through treatment with MBS and bromosuccinimide. However, after the protection, the C4 olefin still did not respond to a conventional hydrogenation conditions. The group then anticipated that deprotection of the hydroxyl group with acid and Li oxidation with TPAP could change the ring configuration to that of 29 and allow the C4 exoolefin to be exposed to hydrogenations, and thus a cationic hydrogenation catalyst with a C3 olefin act with C3 carbonyl acting as a directing group afforded 30, and the protection of the vinyl group with zinc and acetic acid resulted in 2. The oxidation from 28 to 29 also successfully oxidized the lactol to a lactone. The lead group then anticipated to invert the stereochemistry of the hydroxyl group at C8. However, a direct inversion through a Mitsunobu reaction had failed. Fortunately, oxidation of the C8 alcohol to a ketone and a steroid chemoselective reduction fashioned 31 in high yield, and then the C8 hydroxyl is protected with an ethoxyethyl group to form 32. Then, for 32, the group attempted to undergo methanolation with reagents like Eschemoser's salt, formaldehyde, chloroformyl sulfide, etc., but they failed to introduce the olefins at C11. Thus, the group resorted to this four-step formulation, reduction, mesylation, elimination to afford 34 from 32. Then, to complete the synthesis, the protection of the Ca hydroxyl group and esterification with acid anhydride 36, and a final deprotection finally formed Jujuyane. This amazing synthesis of Jujuyane by the Lee group demonstrated their amazing insight into how the structure of Jujuyane can link to the oxidopyridine dimer, and it also shows the underutilized synthetic potential of the oxidopyridine dimer. I hope that this video has been interesting for you, and if you have any questions or suggestions on how this can be done better, feel free to put them in the comments section. The next episode will be about the use of singlet oxygen in synthetic organic chemistry. I hope you have a great day and see you next time. Goodbye.